Again, we are continuing with the portion of viscosity, and specifically, we have to continue with the flow of liquid through capillary. The important thing is that the capillary means a small diameter tube. So, flow of liquid, when we refer, it means for capillary tube, if the diameter is more, we will find the velocity of the flow of liquid will be less, and if the diameter of the capillary tube will be less, then the liquid will come out with a greater velocity. These facts are to be applied, and these facts will continue in the concept of Poiseuille's formula. So now we are first of all discussing the Poiseuille's formula, and Poiseuille's formula is mainly concerned with the liquid flow. So that is, we consider a tube and some liquid flows through that. And whenever we say that liquid is flowing, the viscous forces comes into action, and we find that the flow of liquid is maintained by applying the pressure difference between the ends. So the main concept of the Poiseuille's formula is when a liquid flows through a tube, the viscous force opposes the flow of liquid. So what is basically the viscous force? Viscous force means that there are layers of the liquid, and between the layers there is some friction, and that frictional force between the layers is called the viscous force. Therefore, the viscous force opposes the flow of liquid. Therefore, the flow of liquid is maintained by applying pressure difference between the ends of the tube. Now we further highlight this particular point, that is, Poiseuille determined that if liquid has a streamline flow, now we are using a term streamline flow, it means that it's not turbulent, or we will find that its Reynolds number is less than 2000. So that is called streamline. So Poiseuille determined that if a liquid is a streamline flow, that its Reynolds number is less than 2000, then through a tube, by applying pressure difference small p at the ends of the tube of uniform diameter. So diameter is not to change, because if the diameter will change, we will find that the rate of flow of liquid will also change. So next point is the volume of liquid coming out per second from other end of the tube is given as. Now the formula is V. V stands for volume. Pi is constant, 3.14. P is the pressure difference between the ends of the tube. R is the radius of the tube. Then in the denominator, neta is coefficient of viscosity, and L is the length of the tube. This formula, that is V is equal to pi P R to the power 4 over 8 neta L, is known as the Poiseuille's formula. And here L is the length and R is the radius of the tube, and the name of the formula is Poiseuille's formula. Now we have to check up the effect of temperature on the viscosity of liquid. When we use this term viscosity means the friction among the various layers of the liquid. So how temperature affects the viscosity of the liquid? That is, if temperature rises, we find that the viscosity of the liquid, that is friction, that will be less. So the concept is the viscosity of liquids changes with the temperature, and on increasing the temperature, the viscosity of liquids decrease. That is, the drag or the friction among the various layers will decrease, and the liquid will flow very frequently, or the liquid will flow without any hindrance. Now, Andrade obtained the relation between the viscosity of liquids and the temperature, which is found correct for many liquids. So most of the liquids obey Andrade law. So Andrade law states neta rho power minus 1 over 3 equal to AE C rho oblique T. Here neta stands for coefficient of viscosity, and rho, that is, rho stands for the density of the liquid, and A and C are the constants. T is the temperature at which the liquid is maintained. Now, motion of the body through a viscous medium. So, when we use this term, motion of a body, we consider a sphere, a solid sphere, and we just gently drop it into the viscous medium. Viscous medium means that we first of all consider a tube, or we can consider a container, and in that container we fill some water, and in that water we allow the sphere to drop. Now, this was first studied by Stoke, and hence whatever law was made in this particular observation, that is called the Stokes law. So we proceed with the Stokes law. When a body, that is a sphere, is dropped in a viscous liquid, again we are using a term viscous, means that the liquid is made up of many layers, and between each layer there is some friction among the molecules. So we can't accept a liquid without viscosity. So every time we use the term viscous liquid, that is, friction among the layers is there. Now, due to the motion of a body, relative motion is produced in between the different layers of the liquid. Therefore, viscous force acts in the liquid, which opposes the motion of the body. So whenever we drop a body in a viscous liquid, it is always following some opposition, and this opposition is due to the viscous force. This force increases with the increase of velocity. That is, viscous forces, they increase with the increase in velocity of the body till this force becomes equal to the weight of the body. Being it is a case of vertical motion, so weight of the body can be taken as mg. After this, the body falls with constant velocity, and this velocity is called the terminal velocity of the liquid, or of the viscous liquid. Stoke found that small sphere of radius r, which is falling freely with the terminal velocity v in a liquid whose coefficient of viscosity is neta, is acted upon by a viscous force. So whenever a sphere will drop into a viscous liquid, it will always experience some force, and that force is given by Stoke, and the formula will be known as the Stokes law. This formula is F is equal to 6 pi neta RV, where R is the radius of tube, V is the velocity, and neta is the coefficient of viscosity. Pi is constant, which is 3.14 or 22 by 7. Now, next concept we proceed with, that is, we are taking two symbols, one is rho and other is sigma. Rho stands for the density of the falling body, and sigma stands for, that is, the density of the liquid in which the body is being dropped. So now we proceed with our concept. If a body of density rho is falling in a liquid of density sigma, and the terminal velocity is v, then the following forces act on the body. Number one is the effective force acting downward, that is because of the weight of the body, and that is equal to gravitational force, and that is gravitational force means it is mg. So now m can be replaced by density into volume, so the formula will be W minus buoyancy force U. Buoyancy means upthrust, so the formula can be written as 4 by 3 pi r cube rho g. Basically, rho means the density of the body falling in the viscous liquid. And when we find another formula, that is 4 over 3 pi r cube rho g minus 4 over 3 pi r cube, and now it is sigma g. Sigma stands for the density of the liquid in which the body of density rho is dropped. and g is acceleration due to gravity. So in the whole statement, 4 over 3 pi r cube is common. G is also common. So what we do is we take out common 4 over 3 pi r cube G, and within the bracket we will write rho minus sigma. This is what written in the formula. So now the formula will become 4 over 3 pi r cube into G, and within the bracket we write that is rho minus sigma. Rho stands for the density of the falling body in the viscous medium, and sigma is the density of liquid in which the body is dropped. Now, resistive viscous force acting upwards. When we use this term resistive viscous force, it means we are referring to buoyant force. So buoyant force is acting upward, that is indicated by U in the figure, and downward force is W, that is the weight, mg, and mass of the body can be taken as density into volume, and volume is 4 by 3 pi r cube, and density of the material will be taken as by rho, and density of liquid is taken as sigma. So what now the concept is? Resistive viscous force acting upwards, that is the buoyant force acting upwards, that is indicated by U. In the state, that is F is equal to 6 pi neta RV, where F is the force, viscous force, and is neta, that is the coefficient of viscosity of the liquid in which the body is being dropped, R is the radius of tube, and V is the velocity. In the state of terminal velocity, both forces will be equal, that is they are balanced. So what we have done, we have equated the two values. So what we have done in the next concept, that is 6 pi neta RV equals to 4 over 3 pi r cube into rho minus sigma into G. Again and again I am repeating that rho is the density of the body falling in the viscous medium, and sigma, that is the density of the viscous medium or the liquid in which the body is being drawn. Now terminal velocity can be calculated from the above equation, that is terminal velocity is V, it will be 2 over 9 r square into rho minus sigma divided by neta into G. Neta stands for the coefficient of viscosity. So what exactly we are finding, that the terminal velocity is directly proportional to the square of radius of the tube, and remaining numbers are constant. Therefore, our conclusion is the terminal velocity of a sphere is proportional to the square of the radius of the sphere.